For decades, analog computing had a reputation for being fast but unreliable. Digital computers won out because they could repeat the same calculation with predictable precision. Every value became a string of zeros and ones. Analog machines worked differently. They represented numbers using continuously varying physical quantities like voltage, current, pressure, or resistance. That let them solve certain equations almost instantly, but tiny errors piled up. Components drifted. Precision fell apart as problems grew larger. Researchers at Peking University now say they've solved much of that problem. Their team built a foundry-fabricated analog matrix solver using resistive random access memory, or RRAM. The system experimentally solved 16 by 16 real-valued matrix inversion problems at 24-bit fixed-point precision, which the researchers say is comparable to FP32 digital computing. In massive MIMO signal detection, it reached digital-level accuracy after just 3 refinement cycles. Their benchmarking suggests that with further circuit improvements, this architecture could deliver up to 1,000 times higher throughput and nearly 100 times better energy efficiency than leading digital processors at the same precision. That doesn't mean this prototype can run every AI model 1,000 times faster than an NVIDIA H100. It can't replace a general-purpose GPU. The result applies to specialized matrix equation workloads, and the largest advantage is partly projected rather than fully measured on production hardware. Analog computing has always promised extraordinary speed. What was missing was precision. Why digital computers dominated a digital computer treats information as discrete values. At the lowest level, a transistor is read as on or off. Software then carries out arithmetic through carefully sequenced logic operations. Small electrical fluctuations usually don't flip a 0 into a 1. Digital systems can lean on error correction, repeat operations, and store exact copies of data. Analog systems trade away some of that certainty in exchange for direct physical computation. Picture solving a math equation by building an electrical circuit whose voltages naturally settle into the answer. The circuit doesn't need to run millions of separate instructions. The physics carries out the calculation as signals move through the hardware. But real components aren't perfect. Resistance shifts with temperature. Amplifiers add noise. Manufacturing introduces small differences from one device to the next. The result may land close, but not close enough for scientific computing, communications, or modern AI. The Peking University team tackled the problem by decoupling speed from accuracy. One analog circuit produces a fast, approximate answer. A second analog operation measures the remaining error and corrects it. The system repeats this loop until the solution hits the required precision, what RRAM actually does. At the core of the design is resistive random access memory. An RRAM cell stores information by changing the electrical resistance of a material sandwiched between 2 electrodes. A low resistance state might represent one value. A higher resistance state might represent another. In this experiment, each cell supported 8 stable conductance levels, equivalent to 3 bits of information. The researchers used a 1 megabit RRAM chip for high-precision matrix vector multiplication and a smaller 8 by 8 RRAM array for low-precision matrix inversion. Both were fabricated on a commercial 40-nanometer CMOS platform. This wasn't a hand-assembled device built from exotic lab materials. The chips came out of a foundry-compatible process using 1 transistor, 1 resistor memory cells. An RRAM array can act like a physical matrix. Each cell's conductance stands in for 1 matrix element. Input voltages represent a vector. As those voltages pass through the array, the resulting currents combine naturally according to Ohm's law and Kirchhoff's current law. The array carries out matrix vector multiplication simply through its physical behavior. A digital processor would ordinarily pull data from memory, run through many multiplication and addition instructions, then write the result back. The RRAM array stores values and performs the calculation in the same place, cutting down on data movement and sidestepping much of the conventional von Neumann bottleneck. The matrix problem matrix equations show up almost everywhere in advanced computing. Wireless base stations solve them to separate overlapping signals from many antennas. Some neural network training methods also rely on matrix inversion or related linear system solving. A common form is A times X equals B. Matrix A and vector B are known. Digital methods solve this accurately, but the cost climbs quickly as the matrix grows. An analog circuit can produce a solution directly by placing the resistive array inside a closed feedback loop with operational amplifiers. However, that first answer is only approximate. The challenge is refining that result without handing the important part of the calculation back to a digital processor. Earlier hybrid systems often used analog hardware for a rough estimate and digital floating point hardware for the precise correction. The Chinese team instead kept both major operations in the analog domain. How the two-stage solver works. The first stage carries out low-precision analog inversion because the RRAM devices and their supporting circuits aren't perfectly accurate. The result contains an error. The second stage performs high-precision analog matrix vector multiplication, calculating how far the approximate answer sits from satisfying the original equation. That gap is called the residual. The solver then feeds the residual back into the low-precision inversion circuit to produce a correction. Each cycle nudges the solution closer to the target. The researchers reported that precision improved by roughly 3 bits per cycle, mirroring the 3-bit conductance levels in the RRAM cells. A 24-bit 4x4 real-valued matrix hit the maximum target precision after 9 cycles. Larger complex-valued problems generally reach the same precision within about 10 cycles. This is the central idea. The fast analog inversion doesn't need to be perfect. It only needs to be good enough that repeated analog correction converges toward a precise answer. The design accepts analog error, measures it, then strips it out. Quite different from pretending the hardware is inherently exact. How bit slicing builds precision. A single RRAM cell stores only 3 bits, yet the full system reaches 24-bit precision. It gets there through bit slicing. A high-precision matrix value is split into several lower-precision pieces. Each piece corresponds to a different group of bits and is mapped onto a separate RRAM array. The arrays run their low-precision calculations in parallel or in sequence. Their partial outputs are then shifted according to significance and summed together, similar to breaking a large decimal number into thousands, hundreds, tens, and units. Each piece is easier to represent on its own, and combining the weighted pieces reconstructs the original value. Bit slicing was already a known technique for analog matrix vector multiplication. The harder problem was extending high precision to matrix inversion, where the same simple distributive rules don't carry over cleanly. The researchers got around this by keeping the inversion step low precision while using bit-sliced matrix vector multiplication to compute the correction with accuracy. Block AMC makes the design scalable. A physical RRAM array can't grow indefinitely. Large arrays run into wire resistance, routing complexity, stronger currents, parasitic effects, and amplified noise. So the team used a block-based algorithm called block AMC. A larger matrix is broken into smaller submatrices, with different RRAM arrays holding different blocks. The system runs a sequence of inversion and multiplication operations on those blocks, then combines the intermediate results. Using this approach, the researchers experimentally solved a 16 by 16 real-valued matrix inversion problem at 24-bit fixed-point precision. The relative error reached roughly 1 part in 10 million after 10 cycles. 16 by 16 might sound modest next to giant AI models, but matrix inversion is considerably harder to map into analog hardware than plain multiplication. The point was to show that a precise analog solver could scale past a single tiny hardwired circuit. The block method also opens the door for future systems to rely on several moderate-sized arrays rather than one enormous analog network. The massive MIMO test. The researchers demonstrated the solver on wireless signal detection. Massive MIMO uses many antennas at a base station to talk with several devices at once. The received signals overlap, so the base station has to solve matrix equations to separate the different users and recover the transmitted data. The experiment modeled systems using higher-order 256 QAM modulation, which packs 8 bits into every transmitted symbol, demanding far more precision than earlier analog demonstrations limited to simpler modulation schemes. The researchers sent a binarized image of the Peking University emblem through the modeled wireless channel. Their analog solver recovered the signal with bit error performance comparable to FP32 digital processing, reaching that accuracy after only 3 iterative cycles. This matters because it ties the architecture to a real workload rather than only random lab matrices. Wireless communication, especially future 5G advanced and 6G systems, may demand repeated matrix solving under tight latency and energy limits. Where the 1,000 times claim comes from, the 1,000 times figure deserves some unpacking. The prototype didn't directly beat an NVIDIA H100 by 1,000 times in a full application. The researchers instead benchmarked their analog architecture against state-of-the-art digital processors at matched precision. Their model factored in matrix size, array dimensions, converter overhead, amplifier speed, and block processing requirements. At moderate array sizes, the analog design already showed real advantages for specific matrix-solving tasks. With larger optimized arrays and faster operational amplifiers, the projected throughput advantage could approach 3 orders of magnitude, while energy efficiency could improve by nearly 2 orders of magnitude. The paper also notes that block AMC narrows the advantage as matrices grow larger, since more stages and intermediate operations are needed. Even so, the architecture stayed ahead in the researchers' comparisons. Hitting the maximum projected result depends on better supporting circuits and dedicated integration. So the honest summary is that the demonstrated architecture could reach 1,000 times higher throughput for precise matrix equation solving. It isn't evidence that an analog chip will make every CUDA workload 1,000 times faster. Why this could matter for AI? Modern AI leans heavily on matrix operations, but not every matrix operation is alike. Neural network inference is dominated by matrix multiplication. This chip instead focuses on matrix inversion and solving linear systems, operations that show up in optimization, scientific machine learning, signal processing, and some second-order training methods. An analog solver could become a specialist accelerator. A conventional CPU or GPU would still manage the overall program. When the workload hits a suitable matrix equation, the system could hand that task off to the RRAM solver. The analog hardware would produce the answer quickly and efficiently, then return it to the digital processor. That's a far more realistic picture than expecting analog computing to replace digital machines outright. Digital hardware remains better at control flow, memory management, software compatibility, and exact general-purpose operations. Analog hardware may earn its keep by handling the narrow calculations where physics offers a shortcut. The honest catch. Several engineering challenges remain. The low-precision inversion circuit still relies on external components, operational amplifiers, data converters, switches, and a microcontroller. The larger, high-precision RRAM array was integrated separately, so the complete solver wasn't one compact commercial chip. Scaling the inversion array past the demonstrated size will need dedicated design and fabrication work. Bigger arrays bring stronger currents and more complicated routing. Noise, wire resistance, device defects, and temperature swings all need to stay under control. The system also needs programming and verification steps to place every RRAM cell into the right conductance state. Converters and amplifiers eat into area and energy budgets, and commercial software would need tools that can identify suitable equations and map them efficiently onto the hardware. None of this proves mass production will be simple. My take is that the real breakthrough here isn't simply reviving analog computing, it's making analog error part of the algorithm itself. The first circuit is allowed to be imperfect. The second measures that imperfection. Repeated correction turns a rough physical answer into one that approaches digital precision. That's a powerful design philosophy. Future computers may not have to choose between analog and digital. They may combine both. Digital processors will coordinate the system and preserve programmability, while analog accelerators solve selected equations using currents, resistance, and feedback instead of long instruction sequences. The 1,000 times estimate might shrink once full commercial overhead is factored in, or better integration might let the architecture approach its projected advantage. Either way, this work pushes analog matrix solving from a low-precision curiosity toward a credible specialist technology. So, what do you think? Will analog accelerators become essential for AI, science, and 6G? Or will manufacturing variation and software complexity keep GPUs firmly in charge? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering breakthroughs reshaping computing. because China hasn't built a universal NVIDIA replacement, but it may have solved the precision problem that kept analog computing out of the modern chip era.